Okay, then second type, entropy change for reversible phase transition. You have to find the entropy change delta S for reversible phase transition. This word is very important. Reversible. For example, consider H2O liquid. Reversibly gives H2O vapor. H2O vapor, and the condition is 373 Kelvin or 100 degree Celsius, pressure 1 atm or 1 bar. This condition is very important. Okay, so liquid water reversibly gives vapor water. The condition is 100 degrees Celsius and 1 atm pressure or 1 bar. 1 atm and 1 bar are approximately equal. Okay, so listen, at 100 degrees Celsius, liquid and vapor coexist. That means at 100 degrees Celsius, liquid will be there, vapor will be there. Liquid can be converted into vapor, at the same time vapor can be converted into liquid. There is the equilibrium between liquid and vapor at a temperature of 100 degrees Celsius. So you can definitely say that at 100 degrees Celsius, this is a reversible transition. Okay, liquid can be converted into vapor, at the same time vapor can be converted into liquid. But if the temperature is 101 degrees Celsius, this is not reversible. 101 degrees Celsius, only vapor will exist. Vapor cannot be converted into liquid. Clear. So this temperature and pressure is very important. If the temperature is 101 degrees Celsius, complete water is converted into vapor. There is no equilibrium. Okay, so at this temperature there is a equilibrium present there. So it is a reversible phase transition. In such cases, if it is a reversible phase transition, in such cases, change in enthalpy of transition, it is a phase transition, liquid to vapor, it's a phase transition. So during this process, the enthalpy change for transition is equal to the entropy change for transition is equal to enthalpy change of transition divided by temperature. A very important equation. Okay, only used for reversible phase transition. If the transition is a reversible condition, it's a reversible condition, the entropy change of transition is given by the equation enthalpy change of transition divided by temperature. Okay, right, listen. First case, melting. What is melting? Solid reversibly gives liquid. All are condition reversible. Second case, vaporization. What is vaporization? Liquid reversibly gives vapor. Okay. Third one, sublimation. Solid directly converted into vapor. Okay, so melting, solid, liquid, vaporization, liquid, vapor, sublimation, solid, vapor. Right? So listen, here entropy of melting is also called as fusion. Change in entropy of fusion, delta S fusion, equal to, what is the transition here? Solid to liquid, melting, that is called fusion. Entropy, delta S fusion is equal to change in enthalpy of fusion divided by temperature. That's the equation. Change in enthalpy of fusion divided by temperature. That's the equation. Change in entropy of fusion is equal to change in enthalpy of fusion divided by temperature. My question, whether it is positive or negative. This entropy change positive or negative? That's my question. Delta S is equal to, what is delta S? Final entropy minus initial entropy. That is entropy of liquid minus entropy of solid. Maybe that is positive or negative. That's my question. Delta S is final entropy minus initial entropy. Final entropy is the entropy of liquid. Initial entropy is the entropy of solid. Whether it is positive or negative. You know what is the order of entropy? Gas having highest entropy, then liquid, then solid. So definitely this is positive. Here entropy change is positive. Similarly, what about vaporization? Vaporization. Delta S vaporization, change in entropy of vaporization is equal to delta H vaporization divided by temperature. That's the equation. Delta H vaporization divided by temperature. Whether positive or negative. Delta S vaporization means final entropy minus initial entropy. Final is vapor, initial is liquid. Definitely it will be positive because vapor having highest entropy. So here also entropy is positive. Change in entropy is positive. Then in the case of sublimation, delta S sublimation equal to change in enthalpy of sublimation divided by temperature. Change in enthalpy of sublimation divided by temperature. Whether it's positive or negative. Delta S is final entropy minus initial entropy. Final state is vapor, initial state is solid. Definitely it will be positive. Entropy change will be positive. But suppose in a numerical problem, instead of solid to liquid, liquid to solid is given. Liquid is converted into solid. Okay, solidification. Liquid is converted into solid. In that case, entropy change will be negative. Why? Liquid is converted into solid. Final entropy minus initial entropy will be negative because entropy decreases. So, solid to liquid entropy change is positive. Liquid to solid entropy change is negative. Liquid to vapor entropy change is positive, vapor to liquid entropy change is negative. Okay, so remember that thing. So in general, the entropy change, all these are reversible phase transition. In general, if the condition, okay, the entropy change of fusion is equal to delta H fusion by temperature, entropy change for vaporization is equal to delta H vaporization by temperature, entropy change for sublimation is equal to delta H sublimation divided by temperature. Okay. So listen to a question. For vaporization of water at 100 degrees Celsius and 1 atm. At this temperature, 100 degrees Celsius and 1 atm pressure, there will definitely it is reversible transition. Vaporization of water. Delta H vaporization is given. Temperature is given. So you have to find change in entropy of vaporization. You know the equation. Change in entropy of vaporization is equal to change in enthalpy of vaporization divided by temperature. Right? Change in enthalpy of vaporization is given 66.67 kilojoule per mole, converting into joule into 10 raised to 3 joule per mole divided by temperature 100 degrees Celsius. 100 degrees Celsius converted into Kelvin 373 Kelvin. On solving this, you will get the answer. Okay. 373 Kelvin. So you can find the answer. Simple question. So this type of question also you can expect in the part B section. Okay. Okay, next one. Entropy change for irreversible process. Entropy change for irreversible process. For example, listen. H2O liquid at 1 atm and 298 Kelvin temperature convert into H2O vapor at 1 atm and 493 Kelvin temperature. Definitely it is not a reversible process because initially it is a liquid at 1 atm and 298 Kelvin temperature. It is converted into vapor at 1 atm and 493 Kelvin. Not a reversible transformation. So here, what is the equation for delta S? If it is reversible transformation, you know the equation for finding delta S. But here, what is the equation for change in entropy delta S? That's my question. Okay, H2O liquid at 1 atm 298 Kelvin and H2O vapor at 1 atm and 493 Kelvin. Here, this process passes through several steps. This process passes through several steps. For example, listen. In the first step, H2O liquid at 1 atm and 298 Kelvin temperature converted into H2O liquid at 1 atm pressure to the boiling temperature 373 Kelvin. So convert into boiling temperature. So initially the water at 298 Kelvin is converted into 373 Kelvin, 100 degrees Celsius. Here also the water is in the liquid form. So that is the first step. Okay. In the second step, this H2O at liquid condition, 1 atm pressure and 373 Kelvin converted into H2O at vapor 1 atm and 373 Kelvin. So this is reversible phase transition. So H2O at 373 Kelvin liquid is completely converted into vapor. And the last step, third step, H2O vapor 1 atm 373 Kelvin converted into H2O vapor 1 atm to the final 493 Kelvin. So three steps. Here 3 steps are there. What are the 3 steps? So it's an irreversible process not taking place in a single step. In the first step, your liquid at 298 Kelvin is converted into boiling temperature 100 degrees Celsius. Then complete liquid is converted into vapor at the same temperature. You know, during phase transition temperature does not change. During phase transition, if liquid is converted into vapor at that time, temperature does not change. During phase transition, temperature remains constant. And again, the vapor at 373 Kelvin is converted into vapor at 493 Kelvin. So, in each step, you have to find the equation for delta S1, delta H1, delta U1. What is the equation for delta H1, delta S1? Since here pressure is 1 atm, here also pressure is 1 atm. So it's an isobaric process. During an isobaric process, delta S1, you know the equation for delta S1. Delta S1 is equal to NCP ln T2 by T1. For example, here number of moles is taken as 1. So Cp ln T2 by T1. Cp ln T2 by T1. This is equation number 1. Cp ln T2 by T1. It's an isobaric process. The entropy change for isobaric process we already discussed in the last lecture. Then delta H1. What's the equation for delta H? Delta H is equal to NCP dt and delta U is equal to N CV dt. That equation already discussed in the beginning. Okay, so here N is equal to 1, so delta H1 is equal to Cp into dt. dt is T2 minus T1. Equation number 2. Okay, delta U1 is equal to Cv into dt. So Cv into T2 minus T1. But in case of liquid, Cp approximately equal to Cv. In the case of liquid, but in the case of gas, Cp minus Cv is equal to R, universal gas constant. But in the case of liquid, Cp and Cv are approximately equal. So this will also be approximately equal to Cp into T2 minus T1. So this is equation number 3. So this reversible step passes through several steps. In the first step, delta S1 equal to Cpln T2 by T1. T2 is 373, T1 is 298. And delta H1 is equal to Cp into T2 minus T1, and delta U1 is equal to Cv into T2 minus T1, which is approximately equal to Cp. The Cp for liquid is given in your question paper. Cp for liquid is given in your question paper. Okay, then in the second step, this H2O liquid is converted into vapor. This is phase transformation. Okay, so during phase transformation, the delta S2 is equal to delta H2 divided by temperature, right? Change in entropy of phase transition is equal to change in enthalpy of phase transition by temperature. This delta H2 given in question. This delta H2 is given in question. Delta S2 is equal to delta H2 divided by temperature. So delta S2 is equal to delta H2 by the temperature. Delta H2 given in question. And then what about delta U2? When delta H2 is given, you know the relation delta H is equal to delta U plus delta NGRT. This equation that you studied. Change in enthalpy is equal to change in internal energy plus delta NGRT. Change in number of moles is 1. Delta Ng is equal to 1. Therefore, delta U2 is equal to delta H2 minus RT. So that's about second process. Then the last step, H2O vapor to H2O vapor 373 to 493. Since it is also an isobaric process, delta S3. How we can find delta S3? Delta S3 is equal to Cp ln T2 by T1. Then what about delta H3? Delta H3 is equal to Cp into T2 minus T1. Delta H3 is equal to Cp into T2 minus T1. Then delta U3 is equal to Cv into T2 minus T1. But you know Cp minus Cv is equal to R. Cp minus Cv is equal to R. So therefore Cv is equal to Cp plus R. Right? Cv is equal to Cp plus R. Is it? Sorry, Cv is equal to Cp minus R. Cp minus R into T2 minus T1. That is delta U3. This is equation number 4. Equation number 5, equation number 6, equation number 7, equation number 8. So this complete process taking place in 3 steps. These are the 3 steps. Step number 1, step number 2 and step number 3. In each step you can find delta S1, H1, U1, delta S2, H2, U2, delta S3, H3, U3. Finally, when you add all these three, you will get the entropy change for the total process. This is the total process. So here delta S total is equal to delta S1 plus delta S2 plus delta S3. Delta H total is equal to delta H1 plus delta H2 plus delta H3, and delta U is equal to delta U total is equal to delta U1 plus delta U2 plus delta U3. This type of numerical that you can expect, only numericals. Okay, so a transformation like this will be given in your question. It's a irreversible transformation. A liquid at 180 and 298 can be converted into vapor at another condition. It is irreversible. So you have to find the entropy change for this process, enthalpy change for this process, internal energy change for this process. So the whole process taking place in three step. So find delta S1 H1 U1, delta S2 S2 U2, delta S3 S3 U3. Then finally adding all the three, you will get the total entropy change, total enthalpy change, and total internal energy change. So that's the. I will give you a homework question, then you will get more insight. So a previous question, find out delta H, delta U and delta S for the following process. Here H2O at 180 m 298 Kelvin in liquid state converted into H2 at 180 m 523 Kelvin into vapor state. Definitely it is an irreversible process, and it takes place through three step, and Cp for liquid, Cp for vapor, and delta H vaporization, that is delta H2. Delta H vaporization means delta H2. That is also given in the question. So what is the first step? Listen, your H2O at 180 m and 298 Kelvin in liquid state converted into H2O to the boiling temperature 180 m. Boiling temperature is 373 Kelvin and liquid state. Converting into boiling temperature. Find the delta S1. Delta S1 is equal to Cp. Here both are liquid. So take Cp for liquid. This is liquid, this is also liquid. So Cp for liquid is 36 ln T2 by T1. Final temperature by initial temperature, that is 373 divided by 298, equation number 1. Then what about the delta H1? Delta H1 is equal to Cp into, here also Cp for liquid, 36 into Cp into T2 minus T1, that is 373 minus 298, equation number 2. Then delta U1 is equal to Cv into T2 minus T1, Cv approximately equal to Cp for liquids. So that is also equal to 36 into T2 minus T1, 373 minus 298. Here delta H1 and U1 are approximately equal. This is equation number 3. So this is the entropy change, enthalpy change and internal energy change for the first step. This is a homework question, but I will give you some hint. Okay, so first step. Then write the second step. Total 3 steps are there. Copy the note and write the second step. You have to calculate this. Then second step. What will be the second step? Second step. Your H2O liquid at 180 m and 373 Kelvin temperature undergo reversible phase transition. That means your H2O is converted into vapor at 180 m and 373 Kelvin. During phase transition, temperature remain constant. Okay, so since it is reversible process, your delta S2 is equal to delta H2 divided by temperature. This delta H2, enthalpy of vaporization, is given in question, that is equal to kilojoule, converting into joule 40669 joule divided by temperature. Temperature is 373 Kelvin. This is equation number 4. Okay, so delta H2, that is directly given in the question, enthalpy of vaporization 40669 669 joule, equation number 5. Then delta U2. How we can find the delta U2? Delta U2 is equal to delta H2 minus RT. That is 40669 minus R is equal to 8.314. In joule, the value of R in joule is equal to 8.314 into temperature is 373, equation number 6. So this is the delta entropy change, enthalpy change and internal energy change for the second step, which is a reversible phase transition, right? Okay. Then third step, what will be the third step? Homework question, you have to complete the answer. Third step, your H2O at 1 atm 373 Kelvin vapor converting into H2O 1 atm to the final temperature given in the question is 523 Kelvin. 523 Kelvin vapor. Okay, so here what is the entropy change? Delta S3. Delta S3 is equal to CP4 vapor. This is vapor, this is also vapor. So you have to take the CP4 vapor. Okay, CP4 vapor is equal to 35. 35 into CP ln T2 by T1 ln 523 divided by 373. In most time your answer will be in this form. You ln 523 by 373. It is difficult to find this ln 523 by 373. So in most times, in 99.9 times, your answer will be in this form. 35 ln 523 by 373. Right. Okay. So delta H3 is equal to CP4 vapor. CP4 vapor is equal to 35. 35 into T2 minus T1, right? 523 minus 373, equation number 7, equation number 8. And finally delta U3 is equal to CP minus R. CP minus R, 35 minus R. What is the value of R? Universal gas constant R? 8.314. CP minus R into 523 minus 373, equation number 9. This is the entropy change, enthalpy change and internal energy change for the third step. Okay. Finally, you can find the total. So now you have delta S1, delta H1, delta U1, delta S2, delta U2, delta H2, delta S3, H3, U3. So in your question, find the total entropy change delta H is equal to delta H1 plus delta H2 plus delta S3. Total internal energy change delta U is equal to delta U1 plus delta U2 plus delta U3. Total entropy change delta S is equal to delta S1 plus delta S2 plus delta S3. So that's about the question. So your answer in most times will be in ln form. So you can calculate the final answer. So this type of question, a little bit lengthy question, but when you know the concept, you can easily find the answer. Sometimes delta S1 alone will be asked. Okay, delta S1 alone or delta H1. Combining 3 also you can expect. Then Troughton's law. It's a simple law. Troughton's law, applicable for liquids having no hydrogen bonding. Liquids having no hydrogen bonding and also having boiling point greater than 150 Kelvin. So Troughton's law applicable for those liquids having no hydrogen bonding. Hence it is not applicable for water. In water hydrogen bonding is present. So and also having boiling point greater than 150 Kelvin. In such liquids the entropy change for vaporization, delta S vaporization is given by the equation 10.5 into R. Only entropy change for vaporization. Okay, so Troughton's law is applicable for those liquids having no hydrogen bonding and having boiling point greater than 150 Kelvin. In such cases, the entropy change for vaporization is equal to 10.5 into R, where R is the universal gas constant. And also write a note: no such rule for entropy change for fusion or entropy change for sublimation. In such cases, this rule is not applicable. Only for entropy change for vaporization, 10.5 into R. For example, benzene. You know, in benzene there is no hydrogen bonding, and also boiling point of benzene is 80 degrees Celsius. 80 degrees Celsius is definitely greater than 150 Kelvin. So in the case of benzene, this Troughton's rule is applicable. So what is the entropy change for vaporization of 1 mole of benzene? 1 mole 10.5 into R. For n mole n into 10.5 R. Okay, for 1 mole of benzene, entropy change for vaporization is equal to 10.5 into R. Okay, for n mole n into 10.5 R. So that rule is called as Troughton's law. Another question: the entropy change associated with the freezing. Here freezing is given. What is freezing? Liquid converted into solid. This is called freezing. Right? 1 mole of water at 1 atm and 0 degrees Celsius. 1 atm and 0 degrees Celsius. So definitely it is a reversible process because at 1 atm and 0 degrees Celsius both the liquid and the water coexist. So it's a reversible process. Delta H fusion is, enthalpy of fusion is given. You have to find the change in entropy of fusion, delta SF. Since it is reversible process, delta SF is change in entropy of fusion is equal to change in enthalpy of fusion divided by temperature. Right? So that is equal to delta HF is given, that is 6.01 kilojoule. So 6.01 into 10 raised to 3 joule per mole divided by what is temperature? 0 degrees Celsius. That is equal to 273 Kelvin. 0 degrees Celsius is equal to 273 Kelvin. But one more thing, here the entropy change is negative. Why entropy change is negative? Liquid is converted into solid. Entropy decreases. So put a negative sign. So minus 6.01 into 10 raised to 3 joule divided by 273 Kelvin. On solving this, you will get the final answer. Okay. So since it is a reversible process, how you can identify it's a reversible process? 1 atm and 0 degrees Celsius. At 0 degrees Celsius, you know ice is present, water is present. Water and ice are in equilibrium. Okay. So a nice question. Next section, TS diagram, temperature entropy diagram. Listen. The temperature entropy diagram. Suppose a substance A is a substance. It is a solid at a temperature T, converting into the same substance A converting into vapor state of temperature T dash. You have to plot the TS diagram of this process. It is an irreversible process passing through several steps. Okay, so listen, Here A is a solid at temperature T. For example, ice at minus 10 degrees Celsius. Converting into water vapor at, for example, 400 degrees Celsius. So definitely it passes through several steps. First step, your A is a solid at temperature T, converting into A is a solid to the melting temperature Tm. That means, for example, your ice at minus 10 degrees Celsius is converted into ice at melting temperature 0 degrees Celsius. Then second step, your A solid at melting temperature is converted into A liquid at melting temperature. This is a phase transition and it is a reversible process. Phase transition and a reversible process, because you are at 0 degree Celsius, the ice is converted completely into water at 0 degree Celsius. Then third step, your A is a liquid at melting temperature, that means 0 degree Celsius, converted into A liquid at boiling temperature TB. That means the liquid at 0 degree Celsius is converted into liquid at 100 degree Celsius. That's the third step. Fourth step, your A, which is a liquid at boiling temperature, that means 100 degree Celsius, is converted into A is a vapor at the same temperature TB. Okay, liquid is converted into vapor. That process takes place at the same temperature, 100 degree Celsius. This is also a reversible process. Last step, your A, which is a vapor now at a boiling temperature, that means 100 degrees Celsius, is converted into the, sorry students, here they are the vapor, A at vapor of a temperature, any temperature, that means 200 degree, 300 degree, 400 degree or any temperature. So this whole process takes place in 5 steps, solid to vapor. First step, your solid at a temperature T, for we are taking ice as an example. Ice at minus 10 is converted into ice at melting temperature 0. Then ice at melting temperature 0 is completely converted into water at 0. Then your water at 0 is converted into boiling temperature 100 degree, water at 100 degree. Then water at 100 degree is completely converted into vapor at the same temperature. Then your vapor will be converted into any high temperature. During phase transition, for example, liquid is converted into vapor. This is phase transition. During that time, temperature is constant. This is also phase transition. Salt is converted into liquid. Here also your temperature is a constant. So you have to sketch the TS diagram. Entropy temperature diagram. How you can plot the entropy temperature diagram. Okay, listen. For example, this is the first process, second, third and fourth, fifth process. In the first process, solid at a temperature T is converted into a higher temperature Tm, melting temperature. So entropy, in the first process, entropy slightly increases. This is first process. Entropy slightly increases. Why? Because salt at a T temperature converted into a higher temperature, melting temperature. In the second step, salt is converted into liquid. Solid converted into liquid, entropy sharply increases. So this is the second process. Second step, liquid to liquid, but liquid at 0 degree is converted into liquid at 100 degree. Okay, so again entropy slightly increases. This is third step. Entropy is the disorder. Fourth step, liquid is converted into vapor. Sharply entropy increases. Compared to 2 also, the entropy sharply increases. This is the fourth step. And last step, vapor to vapor, but vapor at T temperature to another high temperature. So here also entropy slightly increases. This is the fifth step. So this is the TS diagram for this whole process. In the first step, solid to solid, both are solid, but as temperature increases, slightly disorder increases. So slightly entropy increases. In the second case, solid to liquid, higher, sharply entropy increases. In the next case, liquid to liquid, but temperature increases, disorder increases. So definitely slight increase. In the fourth case, liquid to vapor, vapor having very high entropy. So compared to 3, 4 having high sharp increase, and last slightly increases. So that's the TS diagram for this whole process. Next, third category. So we discussed the entropy change for ideal gas, entropy change for reversible process, entropy change for irreversible process. Okay, then fourth category, entropy of mixing, of ideal gas. Okay, entropy of mixing. When two gases are mixed, what is the entropy change? Entropy change for mixing of ideal gas. Here the first category, ideal mixing. That's the first category. We have to discuss about ideal mixing and non-ideal mixing. Okay, ideal mixing and non-ideal mixing. So what are the conditions of ideal mixing? First condition, delta H mixing equal to 0, delta U mixing equal to 0, delta V mixing equal to 0, delta G mixing is negative, delta S mixing is positive. Sixth condition, isothermal. Seventh one, isobaric. Eighth one, no chemical reaction on mixing. No chemical reaction on mixing. So these are the conditions of ideal mixing. Okay, so for example, this is gas, this is nitrogen gas having volume 2 liter, plus this is helium gas having volume 3 liter. When they are mixed together, here nitrogen plus helium, if the total volume of this mixture is equal to 5 liter. Okay, in the first container, nitrogen 2 liter nitrogen gas, this is 3 liter helium gas. When both are mixed together, nitrogen plus helium, if the total volume equal to 5 liter, what is the change in volume? Change in volume, delta V mixing equal to 0, delta U mixing 0, enthalpy change mixing 0, entropy change positive, free energy change negative, isothermal, isobaric, and no chemical reaction. No, you know nitrogen and hydrogen, helium does not react. But if nitrogen and hydrogen is taken, they will convert it into ammonia. Okay, so that is not considered. The gases does not react each other. If these conditions are satisfied, you can say that this mixing is an ideal mixing. Okay, is an ideal mixing. Okay, then you have to find the entropy change delta S during this mixing process. Okay, so listen. For example, a mixture containing gas 1 and gas 2, number of moles of gas 1 is N1, number of moles of gas 2 is N2. Here delta S mixing, when 1 and 2, first gas and second gas are mixed together, the entropy change for mixing is equal to, very simple equation, minus R into bracket N1 ln chi1 plus N2 ln chi2. This is the equation. Entropy change of mixing equal to minus R N1 ln chi1 plus N2 ln chi2. Here chi1 chi1 is the mole fraction. Chi1 is the mole fraction. Chi1 is equal to number of moles of first component divided by total number of moles, and chi2 is equal to mole fraction of second component. That is equal to number of moles of second component divided by total number of moles. So this is chi1 and chi2. So this is the equation for entropy change for mixing, minus R into bracket N1 ln chi1 plus N2 ln chi2. Then molar entropy change for mixing. Molar entropy change for mixing. Molar entropy change for mixing. Listen. Delta S mixing molar. Delta S mixing divided delta S mixing molar equation is equal to minus R into bracket N1 is divided by total number of moles. N1 divided by total number of moles is N1 plus N2. N1 plus N2 ln chi1 plus N2 is also divided by total number of moles ln chi2. Okay, N1 by N1 plus N2 is chi1. So the entropy change for mixing molar is equal to minus R into bracket N1 by N1 plus N2 is chi1 ln chi1 plus chi2 ln chi2. So this is the equation for molar entropy change for mixing. Very important question. You can expect numericals based on this. Okay, that's the entropy of mixing of ideal gas. Entropy change for mixing of ideal gas. When two gases 1 and 2, number of moles of gas 1 is 1 N1, number of moles of gas 2 is N2. Then entropy change for mixing is equal to minus R into N1 ln chi1 plus N2 ln chi2. Molar entropy change for mixing is equal to minus R chi1 ln chi1 plus chi2 ln chi2. Okay, so please copy these equations. Okay, once again, what is the equation? Entropy change for mixing of gases, ideal gas, ideal mixing, minus R bracket N1 ln chi1 plus N2 ln chi2. Second one, this is the first equation. Second equation, molar entropy change for mixing. Delta S mixing molar, that is equal to minus R of chi1 ln chi1 plus chi2 ln chi2. Okay, then write a note. Write a note. First note, if I gases are present, here only two gases are there, gas 1 and gas 2. If I gases are mixed, then entropy change for mixing is equal to minus R sigma I Ni ln chi I. This is the equation. Minus R sigma I Ni ln chi I. What about molar entropy of mixing? Molar equal to minus R sigma I chi I ln chi I. This is the equation for molar entropy of mixing. Minus R sigma I chi I ln chi I. So copy the equation. Please copy this equation. Okay. Note 2. Note 2. You know the equation delta G is equal to delta H minus T delta S. Okay. If the mixing is an ideal mixing, you know this delta H is equal to 0. Right. If the mixing is ideal mixing, delta H is equal to 0. So you can write delta G mixing, enthalpy change for mixing is equal to minus T delta S. Or you can say that delta G mixing is equal to minus T into, this is the equation for delta S. This is the equation for delta S. Minus T into minus, that's become plus. So RT sigma I Ni ln chi I. This is one equation. Or you can use delta G mixing equal to RT sigma I chi I ln chi I. So this is the Gibbs free energy for mixing. This is molar and this is Gibbs free energy change of mixing. What is a Gibbs free energy change for mixing? Delta G mixing equal to RT sigma I Ni ln chi I. Molar Gibbs free energy change for mixing equal to RT sigma I chi I ln chi I. So that's about ideal mixing. Ideal mixing. Next question. 1 mole of helium mixed with, so 1 mole of helium and 2 mole of N2 at constant temperature and pressure. Here delta S mixing and delta S mixing molar entropy change for mixing, that you have to find. So find delta S mixing. What is the equation? Minus R into bracket N1 ln chi 1 plus N2 ln chi 2. That's the equation. So that is equal to minus R into, what is number of moles of helium? 1 ln chi 1. Chi 1 is number of moles of that component divided by total number of moles. Total number of moles is 1 plus 2, 3. ln 1 by 3 plus N2 is 2 ln mole fraction is 2 by total number of moles 3. Okay. So that is equal to minus R into ln 1 by 3 plus 2 ln 2 by 3. In most times your answer will be in this fashion. Most times. So minus R ln 1 by 3 plus 2 ln 2 by 3. So that will be your answer. Next question. Find the delta S mixing. You have to find delta S mixing for mixing of 1 mole N2 with 4 mole of N2. So 1 mole N2 plus 4 mole of N2. What will be the entropy change for mixing? So here an important thing, Gibbs paradox. Gibbs paradox. According to Gibbs paradox, if same gases, here both gases are N2, if same gases in same or different amount are mixed together, if same gases in same or different amount are mixed together, delta S mixing equal to 0, delta G mixing equal to 0. This is called as Gibbs paradox, and this was a previous year question of TIFR exam. Okay. Find the delta S mixing for mixing of 1 mole of N2 with 4 mole of N2. Both gases are same. According to Gibbs paradox, if same gases in same or different amount are mixed together, delta X mixing and delta G mixing are equal to 0. In bracket, no other gases are present. No other gases are present. That means, for example, 1 mole N2 plus 4 mole of N2. When they are mixed together, in this case, delta S mixing equal to 0 and also delta G mixing equal to 0. But at the same time, 1 mole N2 plus 4 mole N2 plus 2 mole O2. In that case, delta S mixing not equal to 0, delta G mixing not equal to 0. So that's a Gibbs paradox. If no other gases are present, in such case, delta X mixing equal to 0 and delta G mixing equal to 0. So we completed ideal mixing. Then last case, non-ideal mixing. I think in your school class you studied about ideal solution and the non-ideal solution. Some conditions are there. Similarly, this is non-ideal mixing. Non-ideal mixing means we discussed some conditions for ideal mixing. Delta H mixing 0, delta V mixing 0, delta U mixing 0, isothermal, isobaric, no chemical reaction, such there. If any one of the condition is violated, if any one of the condition is violated, that's called non-ideal mixing. If any one of the condition is violated, that is called as what? Non-ideal mixing. For example, if a gas A having volume 3 liter mixed with a gas B having volume 2 liter, when A and B are mixed together, total volume equal to 7 liter, whether it is ideal mixing or not. Here volume 3 liter, here volume 2 liter, so 3 plus 2 5, but on mixing its volume becomes 7 liter. So here change in volume, delta V mixing not equal to 0, initial volume not equal to final volume, so delta V mixing not equal to 0. So it's an example for a non-ideal mixing. So here what is the equation for delta S and delta A? Sorry, delta X mixing. Two gases, gas 1 and gas 2 are mixed together. Here delta S, entropy change for mixing, is equal to entropy change for 1 plus entropy change for 2. This is the equation. Delta S mixing is equal to delta S1 plus delta S2. Here this delta S1 or S2 can be find out by using the equation. That equation you already studied. The basic equation NCV ln T2 by T1 plus NR ln V2 by V1. This is the equation for delta S in terms of temperature and volume. Do you remember this equation? Delta S is equal to NCV ln T2 by T1 plus NR ln V2 by V1. Or you can use in terms of temperature and pressure NCP ln T2 by T1 plus NR ln P1 by P2. By using this equation also you can find delta S1 and L2. On adding you will get delta S mixing. So that's about non-ideal mixing. So it's a homework question. What is the entropy change for the isothermal mixing? It's an isothermal mixing at 300 Kelvin of what you are mixing? Mixing 33.6 liter O2 with 22.2 liter N2. When both are mixed, final volume equal to 44.8 liter. Whether it is ideal mixing or non-ideal mixing. 33 plus 22, but final volume is only 44.8. When 33.6 liter O2 and 22.2 liter N2 are mixed, final volume is only 44.8 liters. So this case is non-ideal mixing. Non-ideal mixing. In the case of non-ideal mixing, total entropy of mixing is equal to delta S of O2 plus delta S for N2. This is the equation. Okay, then how we can find the entropy change for O2? Only hint you have to work out. Delta S equal to, since it is an isothermal process and temperature, here volume is given. Isothermal as well as volume is given. So you have to use NR ln V2 by V1. Delta S is equal to, for isothermal process, two equations are there, NR ln V2 by V1 or NR ln P1 by P2. Since volume is given, you have to use NR ln V2 by V1. V2 is the final volume. Final volume is 44.8 liter. Initial volume for O2 is 33.6. Initial volume for N2 is 22.6 liter. So you have to practice this question as a homework. Okay, so thermodynamics is basically a numerical based chapter. If you are having any doubt, you can ask that doubt in the doubt section in our app, or you can ask to me. My mail ID (720-110.com) or number. Okay, so you can send your doubt. If you are having any doubt, I will clear that. So the only way to study physical chemistry is you have to practice the previous year question. Practicing many previous questions, then only you will get a thorough idea. So wishing you all the best. Bye.